Dear students, welcome. In this video I will try to explain YOLO. On the right you see a demo of what YOLO actually is. It's a vision application and it recognizes objects in frames, in pictures, and you can use it for video as well. So the acronym stands for You Only Look Once. And it was developed by Joseph, Santos, Ross and Ali, the original version in 2015, but now there's a lot more than the original versions. It's a de facto standard for small applications and it's really easy to work with. There's many different versions, so there's all the time coming out new versions. It's a convolution-based architecture, and it also enables transfer learning. The transfer learning, will come back to that at one of the last slides. It predicts bounding boxes, object type and probability. So basically the green boxes, those are the bounding boxes. The object type is the name which is standing on the top of the box. So apparently I'm a person, which is nice to know. And it also predicts the likelihood or the probability that it really is a person. Okay. Well, before we continue, I just want to explain a little bit about the other videos you can look at before you'll have a look at this movie. Because basically I'm gonna assume that you know already a couple of things. So if you wanna see my whole playlist, then you can click on the left bottom one. On the right top you see an introduction in how neural networks work. I can highly recommend that video. I think it's quite nice to be to say it myself. And the right bottom video is more introduction about convolution. So I'm going to assume that you know how neural networks work, and I'm going to also assume that you know how convolution works. And then we're going to go to the framework. And I'm going to, this whole presentation is based on YOLO 5. YOLO 5 is actually a very old version already, so now we're up to, at the time of the making of this movie, we're up to 12. But the basic ideas are mainly still the same, and it's nice to explain it at a simpler, smaller version. And also the older versions are really open, so you can get all of the data out, which is nice for explanation. I'm basing my a lot of the diagrams I took from this link. I can highly recommend that link. There you see an overview of all the different diagrams. So when we go at the architecture, what do we see here? We see the input image, and then we see a number of convolution layers. And then again convolution layers. There's a lot of convolution layers. And then we see some P3, P4, P5 layers. We'll talk about that. And then we'll go to the final bounding box and predictions. What you see already, we see a backbone, we see a neck and a head, and that is still present in the current versions of YOLO. When you talk about transfer learning, I will talk about it at the end. But basically, you can retrain the head if you want to do transfer learning. You can also retrain other stuff, but that's just retraining the head is the simplest. So let's go into a little bit more detail. So here we see for YOLO 5 all the steps. We see at the gray image, let's take my mouse here, we see the image coming in, and then it follows a lot of convolution steps and C3 and CBS, and well, we'll talk about that, all that things, and SPPF and concat. But we also see like not sections, but the information is not only going linear through the flow, but also takes a jump. Okay. And then in the end, we'll come to the head. I will explain already now that the backbone and the neck is basically just transforming the image in new pictures with information, where you have all kind of the I'll explain a little bit better, but like we'll see it transformed being all information about angles, for instance, or if there's circles in the image, etc. The real object recognition takes place in the head. So all this stuff is pre-processing. Okay. What we could do, we could draw a snake through this picture, like how does the information flow, and of course then we're disregarding the little cross overflows. And we could put that in a linear fashion, and then I'm gonna talk through all the steps. The diagram I showed you before was all the numbers in it is for the YOLO 5M, the medium-sized YOLO model. I'm going to show you the results for the small model, not the nano, but the small model. So yeah, the numbers will be a little bit different, like the amount of features and stuff like that. So we'll start with this image. This is me. I think this is Spain actually. And we'll try to predict objects in this image. And we'll see how this image flows through all our, the whole snake basically. So we'll start at the top, and the first step is a convolution layer. And basically what you see already, it translates each picture to another picture. And that's done with all different convolution filters. And you see already that from each picture we get different information from the image. So that's the convolution layer. It works with a, and I explained already in the other video, it works with a convolution kernel, and this is just an example. And the kernel goes over each pixel of the image, and it uses this kernel to do a convolution, and then you get this result. It's not the only thing it does. It also does a CILU function, so that's like a ReLU function, but with a little bumper at the bottom. So that's a little bit sigmoid behavior. So it does a convolution, but it also does an activation function. Okay. Then we go to the next step, and we see again a convolution, but we also see that the number of features goes from 32 to 64. That doesn't fit on my image anymore. So what you basically should think about is that here there's a lot more images still. So now we're up to 64 features. And again, you see the difference with the last one. Hey, it changed again. Then we're gonna do a C3 step. And the C3 is actually, it's combining multiple convolution filters. I'll show a small diagram like here. It's combining multiple convolution filters, and it's also throwing away some information with skip connections. No, that's not true. It also is inputting some information from a previous step. Okay. Then we have another convolution layer, and you see that the number of features, we will call one of this rectangle, one of these images, we'll call a feature or a channel. So we see that we're already up to 128 features, so actually I have two less image space, two less display space. Then we're going to do again a C3, then we're going to do convolution, and you see already that the information is really like, I don't know what this information is anymore, right? What does this picture mean? I don't know. It's the result of all those convolution layers, I don't know. But apparently it encodes something useful. Then again a C3, then a convolution, then a C3, and then we'll get something else. We're going to do spatial pyramid pooling. Pooling is throwing away numbers, or basically clustering numbers, like you take a 2 by 2 amount of numbers, or 5 by 5, and you only save, for instance, the biggest one, or you save the average one, and stuff like that. That's pooling. So what you see here, that we're also pooling on different scales. So this is scaling on a big scale, smaller scale, and even a smaller scale. So that's the spatial pyramid pooling. We'll come back to that, because when you look at the original picture, you saw already a big person standing there and a small person. So we want to be able to recognize objects on different scales. Okay. the next convolution layer. Then we're gonna upsample. You see that it doesn't really change. It changes visually, but we're just making more pixels. Then we're gonna concat. That's a new step. And basically, what we're gonna do. This is the first. Let's see. This is the first concat we had. We have the previous information, but we're gonna concatenate. So stick it at the end, basically, the other information of the previous step. So now we're actually making a bar graph. And you don't see it in the image changing, because this image was pretty the same as this one. But what actually happens is that it concats at the end. So this one doubled now. And you see that also. You go from 256 features to 512. Okay. Then we have another convolution layer. We do see that the number of channels or features goes down. It goes down again, convolution. Then we upsample again. Then we concat. We concat here. Then we have again a convolution. And you see that, well, I cannot recognize a guy on a bike anymore, right? It's transformed in information, but I don't know what it is anymore. Then we get a concat. This concat, then we get a convolution, then we get a concat, this concat, the last one, and then a convolution, and then we're done. So basically what we did now is this whole first part, so the backbone and the neck, and now we're going to take the information from here, right, because we're going to see what inputs in the head. So the head 0, the left one is called head 0, is going to steal the information of the output of this convolution filter, and it's basically also happening here, and it's also happening here. And you see already that it takes from different parts of the whole chain, it takes information. Okay. Then we're going to look at what did it do with that information. Let's see the first one. Apparently the first one, and now we have all the information. It made the head 0, it made a lot of channels features. Well, not that many actually, it's 8 times 16, so that's 128. And the maps here, you don't see it that much, but there's a lot of pixels in these maps. So there's big maps, but not a lot of channels. So basically we're looking, for each channel we're looking at really the details. So this is the fine detail in the image. Then we go to the head 1, and here you see that I'll go back, you see that the pictures, the rectangles are a little bit smaller. That's true. Now we've got medium-sized maps, so a little bit less pictures, but we've got more channels. The amount of maps, the amount of features is bigger. So we're now looking at the picture with a little bit more bigger scale. Then we go into the last head 2, and then you see the same effect. Now, the picture itself, the small rectangles, there's not a lot of pixels in it, so it's small maps, but there's a lot of channels. And all of these channels represent some kind of information, some kind of feature of that original image. And what kind of information? That's quite difficult. You cannot see that with a CNN wheel. With a simple convolution, you can still see it, right? Because like sharpening filter gives the edges of an image. But what you see already, you've got a pipeline of a lot of different convolution kernels, so we've got no idea anymore what each image represents. But we don't need to, basically, because that's a lot of time with neural networks. The neural network knows what it does. It's kind of a black box. Okay. So we've got these 3 maps, and now the next step, we're going to see what is really the purpose of the head. It's predict the output. So we're first going to look at what does it actually predict. Well, there's actually, I think 80, with YOLO 5, 80 different categories which it can predict, and which the head is trained on. So now the head is really trained on predicting these classes. So what we had until now was just transforming the whole picture into feature maps. And now we're going to see the next step is, okay, but how do we get from the feature maps to predictions for this type of objects, including the bounding box and the probability? So that's a quite big step. if we look at the output of my picture, you see that it gives something like this. So we see the bounding boxes. It's actually quite accurate, I think. Maybe the person is a little bit too high, but that's okay. So we see person, we see 2 persons being predicted. We see a bicycle, 3, 4 cars and 1 truck. And we see for each object which is predicted, we see the probability that it's right, that there's really a person there. And we see the coordinates of the bounding boxes. So the big question now is, how do we get from this to that previous picture? And that's the second part of this presentation, basically. So what we're going to do is we're going to first look at only one of those feature maps. So we're going to extract one feature map, because if we can explain it for one feature map, then we just copy paste and then you've explained it for everything. So one of those channels or features is basically one map, and it depicts something. It could be like how many circles are in my image or whatever. What it really is a little bit fuzzy. It's not that, like, it's never as simple as how many circles, but it does tell you something about the properties of the image. Okay, so what we're going to do with this image map, we're going to divide it. This is the image map, and you see already that the small image map, the head 2, was indeed low resolution, right? Not a lot of pixels. Now what we're going to do, we're going to step through all of those pixels of those different heads. And you see already that for head 2, that's a lot less pixels. But we're going to step through and we're going to do our trick on each of these pixels. And what you also see is that there's like here already some bounding boxes. Those bounding boxes are called anchors. And that's basically different reference frames. And we're going to see a little bit about that. And it basically means that the next calculation what we're going to do is looking at different scales, basically. Okay. So what we're going to do, we're going to take this value of this pixel, and it's dependent on the x, right? On the x position, on the y, but also on the channel. So which feature map are we looking at? But also on the head, right? Because we've got 3 different heads. Okay. So C is the channel number, H is the head, and we're going to use a convolution, one convolution, one-on-one convolution, actually quite simple. It's basically multiplication, and it looks like this. So this is the heart of that next step. So what do we see? We see here already some kind of a bounding box explanation, not explanation, but a prediction. So, and basically these are the coordinates in the anchor. It's basically the coordinates in this box. So it tells you what is the position versus that pixel you have, but it also tells you how big he thinks, or it thinks, how big that object is. Next is the confidence. So is there an object? Is there an object at all? It could be there's no object at all. And next, it tells you the likelihood for each type of object. So if there's an object, is it probably a person, or is it more a car, or whatever? So this is the outcome. This is what comes out of it. And how do we calculate that? Basically with 2 vectors. This first vector is dependent on the channel, the head, and the anchor. And so we multiply that times the value of the pixel and the bias factor. Bias factor is just the offset, and the bias factor is dependent on the head and on the anchor. It's not dependent on the channel anymore. Okay. So if we continue, these weights, those 2 vectors you see there, that's basically that's where all the intelligence of the head is encapsulated. That's where, when you train it, those vectors we train. So that's the idea. If we've got the correct vectors, then we can indeed predict the right vector at the end. Now this is it's a little bit difficult to understand, so I've made first we're gonna tell you quickly about how many parameters are in those vectors. And when you look at it for for YOLO 5, it's already 200,000 parameters. So you can stuff a lot of information in this. Okay. Next step. So I'm going to explain a little bit better, but also making more like an assumption, but I will explain. So what really is going on in one channel. And for that, I'm going to do a gross oversimplification. So let's say you've got one channel and it predicts hands. And it doesn't work like this, because the real features are much more subtle, and it's not so simple like, oh, I predict hands. But it does predict something about that image, and it predicts something about where properties of that image are in that image. So let's make the simplification. Okay, we've got a vector which kind of tells you something about the hands. Then how would the next step look like? How would that vector look like which predicts it? Well, I've of course made some liberal assumptions here, or some liberal freedom. So basically, let's assume that this is the vector. So if we've got a 1, it calculates the x1 is going to be -0.7, the y1 is 0, the y2 is 3, the confidence level is 0.5, and if he sees hands, he thinks it's probably a person. Well, that's not a strange assumption. If you do that, so this is, and basically this vector belongs to this type of feature, right? For each different feature, we need a different type of vector. And some of the features will be better at predicting a car, some of the features will be better at predicting a person, which is also what you expect. If we look at the outcome, then this calculation will give this kind of bounding box prediction, right? And then we can put that in our picture. And then we'll see that you have got 2 bounding boxes. This is the basic, and again, I'm taking some liberties here, but basically this is the key idea of how that head prediction works. And for instance, if we would have a different feature map, something which would predict like 2 circles, again, this is a gross oversimplification, then we would probably have that vector for this channel predicting a bike at that place, right? Because, well, 2 circles could be a bike. So then you get something like this. Again, this gross oversimplification, but this is the basic idea how it really works. The features are a lot less defined, and these vectors, of course, are also not like a nice 1 here and 0, 0 on the other stuff. So it's a lot more fishy, but this is the basic idea. Okay. And I'm going to show you how that works. And this is actual real data of all those different feature maps where the person I selected now only all the bounding boxes where it predicted a person, and then you see that it predicts in all those feature maps, and I've got a small person and a big person, and you see also that the small person is better detected in head 1 and the big person is better detected in head 2, which also makes sense when you look at the size of those and the resolution of those boxes or feature maps. So basically what it does, what is shown here is when it's more white, the probability is bigger. And if it's like a darker red, then the probability is lower. So you see that in each image, and that's not true actually, because I only am showing the channel, the feature maps, and you see that it skips a lot of feature maps where it has predicted a person. So in a lot of feature maps, it didn't see a person at all, which is kind of logical, right? If you're looking for circles in your image, it doesn't have anything to do with a person, so that makes sense. Okay, what we could do is show all of those different feature maps for a person in the image, and then you see where it gets its final result from already. And you see that it's got too many feature maps, so we'll talk about how does it cluster those feature maps, because it does some tricks there. So this for the person, you see the biggest values, it senses around me and the person standing behind me. When we look at the result for the bike, you see that there's a lot of big white rectangles around my bike, and some different size red also about me, so he thinks, yeah, you're a little bit a bike as well, which is quite not true, but okay. And the last one for the car, and you see that the car, and it's maybe you have to look at the right side of the image there. There's a lot of cars actually standing. But he also thinks the bike looks a little bit like a car. Okay, so we still have to filter this and see which bounding boxes are really relevant and which are not. So then we're going to come to the next step, the non-maximum suppression step. It's first sorts and filters the boxes on confidence scores, so then you lose already a lot of boxes you saw in the previous images. Then it calculates the IOU, and that's the intersection of a union. So basically it calculates how much overlap is there between boxes and how big is the combined area of the boxes, and that's the ratio between those two. And if the ratio is big enough, then he thinks, well, it's probably the same object, right? That makes sense. And it's repeating this process for higher scoring boxes. So it still tries to minimize the number of boxes because, yeah, what you saw already in the previous picture, you get a lot of double scores. If it applies this mechanism, then you see that it ends up with these predictions, which are quite nice, I think, quite nice. And then we're basically to almost already the end. So what did we do? We explained YOLO, I think, but we still skipped one step, like how did the transfer learning work? And that's quite important because the transfer learning is how you're going to use it. You're going to use it to not only, probably you're going to use it to not only predict people, but maybe you want to predict swimming pools or something else. Okay. So, how does transfer learning work? And it's actually quite simple. The head is the connection between the features, the channels, and the objects. So, if we retrain the head, we have a custom application. And the only thing we need to retrain the head is have a lot of pictures with the objects and the bounding boxes. So, you have to have a lot of pictures where you already said, there's the object with this rectangular around it. And that's the bounding box. And if you've got that, then the step of retraining that head is actually quite simple. I'm not explaining it here. You can find a lot of tutorials online. So, then we come to the end. I hope I gave you some feeling of how YOLO really works. For me, it was a fun journey, so I hope it was useful for you as well. Bye-bye.